Engineer Courtney, I make a short presentation about the webinar.
Okay.
Perfecto. Sí que se nos pasa el tiempo rápido. Bueno, este webinar es sobre radioaficionados en Marte. Vamos a presentar a nuestro invitado, que es el ingeniero Courtney Duncan. Tiene sus indicativos November 5 Bravo Foxtrot y vamos a hacer una pequeña reseña del ingeniero. Courtney Duncan tiene sus comienzos como radioaficionado en Texas, donde obtiene pues un título como pues interpretación musical en piano, ¿sí? Más adelante es titulado como ingeniero electrónico y logra una carrera en el Jet Propulsion Laboratory, JPL, asociado con la NASA y el Caltech en Pasadena, California, que su trabajo consistió en todo lo que era sistemas de radio de vuelo para naves espaciales que van a Marte y más allá. Ahora él está jubilado y después de 30 años está activo como presidente de la Sociedad de Microondas en San Bernardino, operación y competencia de microondas para aficionados y rebote lunar. ¿Listo? Entonces, Mauricio, ¿estás listo?
Sí, Ricardo.
Ok, vamos a arrancar con el tema de preguntas. Bien. Engineer Courtney, I was a group of question about the all experience with the systems to radio communication into Ingenuity helicopter in Mars. Yes?
Right.
Okay. First one in Spanish, and my friend Mauricio translate for you can respond about these questions.
Okay.
Primero que todo, ¿desde hace cuánto eres radioaficionado?
Hello, Courtney.
Morning.
Okay. For how long have you been an amateur radio operator?
Let's see. I was first licensed in 1972, so it'll be 50 years next March.
Okay, a lot of time now.
Yes, it's amazing how fast it goes by.
Yes. I'm an amateur radio too. I'm Hotel Kilo 4, Quebec Yankee Echo.
Ah, good.
Ricardo, 50 años.
Sí, bastante.
Desde 1972.
Claro. Fundador, mejor dicho, de todas estas nuevas tecnologías. Segunda pregunta. ¿Qué es lo que más le gusta de la radioafición?
Courtney, talking about everything you can do it with the ham radio, what is the most exciting part for you?
Well, there's so many different things you can do. I think in modern times, or in the last several years, I've been active on Earth, Moon, Earth, doing moon bounce on 1296, the 23 centimeter amateur band, and that's it's a very technically complex operation to do that, and once you get a success, it's pretty good. I've been doing it for about 5 years, and I've had about 1,000 EME contacts.
Yes.
And yeah, so that's the thing lately. This picture you're looking at here is part of our 10 gigahertz operation. We have a contest in the United States, 10 gigahertz and up, every August and September, and that's a picture of me operating from San Diego, making contacts up north. We work 300, 400, 600 kilometers on the 3 centimeter band, 10.368 gigahertz.
And what kind of setup do you have for 1296? You have also parabolic dishes, and what kind of equipment do you use for that EME contacts?
Yeah, it's I have pictures someplace, but it's a 3.8 meter parabolic dish, about 6 meters high. You know, it doesn't need to be very high because you're pointed up into the sky.
Yeah.
And I have a solid state amplifier that runs about 350 watts. And the way we say on EME, how much power at the feed, because the losses are high. So it's like 250 watts at the feed. And then I use a Bulgarian transverter to go up from 2 meters to 1296, and then I use an IC705, an ICOM rig, as the intermediate frequency rig, and everything there, you know, CW and WSJT modes and even sideband are done from there.
Are you able to, with that kind of amplifier, are you able to do all the modes? Can you hear your CDW?
Yes, I can. My criteria when I built the station was to be able to hear my own echoes, and so it had to be kind of in the 3 meter class to do that. But because if you can hear your own echoes, then you can debug your problems without having to involve people all over the world at inconvenient hours, right?
Yes, right.
So yeah, I can hear my own echoes, and mostly we work digital modes because a lot of the stations are smaller, and that's all you can do. Yes. But with the larger ones, with the ones as large as I am and larger, we also do CW, and that's fairly common.
Pretty nice. Let me translate, please. Bueno, Ricardo y compañeros, entonces lo que más le gusta a él, digamos, de los últimos tiempos es hacer el rebote lunar, que es pues de las cosas más interesantes que puede hacer uno como radioaficionado. Él está trabajando en la banda de 23 centímetros, que es 1296 megahertz. Yo le pregunté qué equipo tenía, me contó que tiene una parábola de 3.8 metros y tiene un amplificador de 350 vatios. Eso es un transverter, o sea, él trabaja en 2 metros y con el transverter y el amplificador pues tiene más o menos 300 vatios en el feed a la antena. Él dice que con esa, es que 350 vatios es mucho para esa frecuencia. Él puede oír sus propios ecos en la luna con el software digital y trabaja los modos digitales. El WSJT, que es el que se usa para esta modalidad, y tiene aproximadamente 400 contactos alrededor del mundo en esta banda, Ricardo.
Perfecto, no, impresionante, ¿no? Igual para hacer M tiene que tener bastante potencia y 300 vatios es muy común. Si mal no estoy, pues es la imagen, la antena la vemos en la imagen de la presentación.
Ah, bueno, sí, se me olvidaba. Esa antena no es de 23 centímetros, esa antena es para 10 gigahertz, que ellos también hacen contactos en 10 gigas. Entonces, ese setup que le está mostrando ahí, ese es él, ese setup es para 10 gigahertz.
¿Para 10 gigas?
10 gigas, sí. La banda de 10 gigas para radioaficionado, que también es muy común ver rebote lunar en esa banda.
Pues sí es una de las prácticas, sí, por la alta potencia, pero alta frecuencia sí no estaba tan familiarizado, ¿no?
Sí.
Ok, bueno, sigamos. ¿Cómo se adicionó un equipo de radioaficionados al proyecto de las comunicaciones del helicóptero Ingenuity con el JPL?
Primero explícame a mí qué es eso para yo poder explicar. ¿Qué es el JPL?
El JPL es el Jet Propulsion Laboratory, uno de los grupos asociados o que integran todo lo que es la investigación al espacio, ¿sí? Y digamos que son los encargados de toda la parte de robótica, sondas de exploración en general, ¿sí?
Sí.
Y el Ingenuity es el dron helicóptero coaxial que está haciendo tareas en Marte, es el primero que envían. Y el tema de hoy, o por el cual hablamos de radioaficionados en Marte, es porque el ingeniero Courtney, con todo su equipo,
Sí.
todo el sistema de transmisión entre el helicóptero y el robot. Curiosity, el Perseverance, perdón, el Curiosity fue anterior.
Ah, ya.
¿Sí? Entonces, lo que vamos a tratar hoy fue precisamente ese proyecto. ¿Cómo fue el diseño de ese sistema de comunicaciones? ¿Cómo fue la experiencia entre un dron, sí, volador? Pues en este caso, bueno, valga la redundancia, o casi todos tenemos el concepto de drone, que es el tipo que vuela, pero también tenemos equipos de tierra, en fin.
Sí.
Pero en este caso, pues estamos hablando de un sistema que fue transportado en el rover, fue desplegado, luego fue puesto a volar y que transmite todos sus datos, toda su telemetría en transmisión-recepción con el Perseverance, el rover que está también haciendo tareas.
¿Y eso es en banda de radioaficionado?
Eh,
¿O no
no,
sabemos?
no tanto en banda, no, pues sí, utiliza, no, espérate, esa parte es lo que le vamos a preguntar.
Ok.
Entonces, vamos a preguntar es, ¿cómo se
¿Cómo lo
adicionó un
diseñaron?
equipo de radioaficionados a ese proyecto?
Okay. Courtney, we would like to know, I was talking with Ricardo about the project of the Ingenuity, the helicopter, and we would like to know how did you design the system, the telemetry system between the rover and the helicopter?
Right. So the main constraint on the helicopter was that the everything on there had to be as low mass as possible.
Yeah, the
So we
way.
had, I was given 10 grams to put a radio and an antenna on there. And so we decided to use a commercial part that is in the industrial, scientific, and medical band. These are commonly available and they're low cost and they have well-developed protocols. The one we used is the Zigbee protocol. That's IEEE 802.15.4 standard, and these are commonly used for home automation systems and so forth.
Yeah. Heard of that.
Right. So we had this part that weighed about 5 grams, and then we did some work on it. We took some things off of it. It ended up weighing about 3 grams, and that was the main driving thing. The other thing is we wanted to maximize the range, and so we picked the lowest ISM band that we could get a part for, and that was 900 megahertz. You know, there's ISM bands at 900 and 2.4 gigahertz and 5.8 gigahertz. There's several that are higher, but we knew that we were going to use an omni antenna on both ends so that we wouldn't have to point anything and we wouldn't have to care which way the rover was parked or which way the helicopter landed. And so we knew we were going to use an omni antenna, and so the path loss is lowest for the lower frequency.
Of course, yes.
If you went much lower in frequency, the antenna would start to get big. So the antenna we have on the helicopter is about 5.5, 6 centimeters long. It's just a quarter wave whip. And so we use the 900 megahertz, and we also got the high power part. High power, in this world, means 1 watt. Okay. So it's about a 1 watt transmitter at about 900 megahertz with a simple omnidirectional antenna on both ends. And so far we've had the goal was to be able to communicate up to 1 kilometer. And we have had cases where we've gone 700 or 800 meters successfully. It's kind of near the edge of the range, but it has worked. And you know, with digital things, it works until it doesn't, and then it just doesn't work. And so, right. So it's worked fine down to there, and we've dropped a few packets toward the edge, but it's largely been satisfactory for that purpose.
And what about the communication protocol? Are you using the standard Zigbee protocol, or you have another kind of protocol?
Well, we modified the protocol. So for the physical layer, the packets that 802.15.4 specifies, we use those packets. But what we did, we changed the protocol to be suitable for our uses, and there was a couple of things we had to do. One is the helicopter has to remain radio silent until it's spoken to, and that's not generally the way that it's done on Zigbee or any other digital protocol. But what we did, we came up with what we call beacon mode, where the base station on the rover, on the Perseverance rover, it would turn on and it would start sending packets that we call beacon packets, And then when the helicopter would turn on, and when it heard these packets, it would start responding. And so that's how we controlled the helicopter not transmitting unless it was told to. And so then it would respond to these packets, and then the base station on the rover would take control, and it would say, okay, you're allowed to transmit packets in these time slots, and I will transmit packets in these other time slots. And by assigning out the time slots, it was able to move data in both directions the way we wanted it to. And of course, most of the data wants to come back from the helicopter. That's where most of the interesting information is. So 90% of the slots are assigned for the helicopter to send data back to the rover.
Very nice. Let me translate. Bueno, entonces básicamente es esto. Obviamente por la disponibilidad de peso era muy baja, pues porque por obvias razones. Entonces ellos les dieron 10 gramos para el equipo transmisor, hablando del helicóptero. Antena y transmisor. Entonces ellos optaron por partes comerciales, una tecnología que me imagino que ustedes la conocen, que se llama Zigbee, que son transmisores receptores generalmente en 2.4 GHz, pero ellos lo trabajaron con la banda ISM de 900 MHz, porque querían tener las menores pérdidas posibles. Todos sabemos que a mayor frecuencia pues las pérdidas son más grandes. Entonces trabajaron con la banda ISM de 900 MHz y el transmisorcito pesa 5 gramos. Ellos pusieron los módulos Zigbee tanto en el helicóptero como en el rover y tienen antenas omnidireccionales de cuarto de onda para 900 MHz con una potencia de 1 vatio y tienen un alcance efectivo aproximadamente de 1 kilómetro. Yo le pregunté sobre el protocolo, ellos me dicen que el protocolo, Zigbee tiene un protocolo establecido, ellos lo modificaron para adaptarlo pues a sus necesidades y meterle pues lo que ellos necesitan, la información que necesitan transmitir, y aparte de eso también modificaron el helicóptero para que no transmita de modo continuo, sino que lo haga solo cuando el rover lo interrogue. Ricardo.
Correcto. Pues ahí saltamos de una vez a la parte técnica, pero la pregunta que se hacía era el por qué el JPL, sí, una entidad pues gubernamental, científica, pide ayuda a los radioaficionados. ¿Por qué pidió ayuda a esos radioaficionados y cómo Courtney armó su equipo de radioaficionados?
Okay, Courtney. The other question is we have a question because we would like to know why the Jet Propulsion Laboratory asks the ham radio, the ham people to help them in this project. Why is that?
Well, it was So at Jet Propulsion Laboratory, we do a lot of the charter is to do deep space missions, and therefore part of that, of course, is deep space communication from the Deep Space Network out to all the different interplanetary probes going different places. And generally, these, we have standards that we use, and we have processes to build the radios and protocols that are used to transmit data over the air.
Uh-huh.
But these are generally they're customized to the mission, because the missions go to different places and they go different distances and they have different data rates available and so forth. And so you really have a telecom system engineer come on board in every mission and design a system that's kind of optimized for their needs. Now, when we were going to do the helicopter telecom, the whole approach was going to be different. Because the JPL doesn't have any radios that are a few grams. The smallest radio we make for deep space use is the Iris transponder, which is intended for deep space CubeSats. And in its standard configuration, it's about 400 grams, and it's about 0.4 liters in size. And that's about the size of the entire helicopter. So so it was not possible to have one of our standard radios that we understand how to do and that uses our standard protocols.
Yeah.
And so what we had to do, we had to just we had to do what a ham would do. A ham would go out and say, well, this thing, this Zigbee part kind of looks like something that we could make, we could hack into use for this, right?
Yeah.
And so it was basically our ability to take things off the shelf and modify them to our specific needs without having to do too much to it. And hams are pretty good at that, right? This is kind of what we do for a hobby anyway. We don't build things from individual parts so much. We take things that are surplus or that are intended for one use and use them for another. so that was kind of the reason it was done, and this was also a kind of a ham radio like project. It was we're trying to set up a communication system to go over a short distance for a specific case, and those of us who do microwaves and ham radio, this is what we do. We go a kilometer or 10 or 100 kilometers. Yes. On some frequency just to show that it can be done, and so that's kind of ham-like too. So it's kind of the practical, hands-on experience and aptitude that we have that which was why they asked us to do this special thing for them like that, right?
Yeah, that special project. And how do you choose your team? The team that is working with you in this project. How do you choose?
It's not like the way staffing works at JPL is that you're assigned projects based on who has needs and who has money, who has resources to pay you right now. Uh-huh. And so it's not like we get to pick from among everyone who would be ideal for this. It's like we get to pick from whom is available right now, or in a case where one person is really needed, we can negotiate with the projects that they're working on and get some of their time. Typically, what happens and what happened throughout my career was that you would be assigned to 3 or 4 projects at once, and you would work quarter time or 1/3 time on each one, just based on the deadlines that they had or whatever the needs were, and this keeps everybody pretty busy. You'll have interleaved things, and sometimes deadlines all come at once, and everybody works a lot. But the short answer is that there's several people in the flight radio section where I was working who were hams or who had that kind of mindset, and we kind of went down and found people who were available who could do these things, and we work with them. And I think overall the team was about 10 part-time people over 3 or 4 years that we did this. There was 3 or 4 of us who went all the way through, but no one ever worked full time. It was kind of quarter time or half time at most. Most of the time we were working on it.
Okay, let me translate. Bueno, entonces él me dice que generalmente a estos proyectos, Ricardo, ellos utilizan comunicaciones, pero de deep space, es decir, de muy larga distancia. Entonces ellos trabajan generalmente, los ingenieros de telecomunicaciones están especializados en equipos, en antenas gigantes, en equipos con mucha potencia, con amplificadores pues de señal, porque están trabajando deep space, o sea, distancias demasiado largas. Entonces, como este era un proyecto diferente, que es un proyecto pequeño, de corta distancia, digamos, no complejo, porque ellos no tenían que diseñar el sistema como tal, sino utilizar, digan, partes comerciales. Entonces, por eso, como es algo tan común en los radioaficionados, por eso los invitaron a ellos a ser parte de este proyecto. Y él me dice que el equipo, pues que él no lo escoge como tal, sino que en el JPL, pues hay mucha gente trabajando en muchos proyectos simultáneos, y en este proyecto con él están trabajando alrededor de 10 personas y trabajan es part-time, o sea, dedican cierto tiempo a cada proyecto y pues en el proyecto este específico son 10 personas que colaborando pues en esta parte.
Perfecto, Mauricio, muchas gracias. Sí, ya se entiende por lo que pues entendemos la calidad y la cantidad de ingenieros que tienen allá en el JPL. Entonces la pregunta era cómo se logra participar directamente por parte de un grupo de radioaficionados en estos proyectos. Pero vamos avanzando, no hay mucho tiempo. Bueno, este es el recorrido del Perseverance con el Ingenuity. La pregunta puntual es, ¿cuál es el rango máximo que calcularon de comunicaciones entre el Ingenuity y el Perseverance? ¿Cómo lo calcularon teniendo en cuenta que está en otro planeta? O sea, ¿qué variaciones tuvieron en cuenta o pronto planearon o qué se podían esperar al ir a trabajar en otro planeta para saber que el rango de comunicaciones que tenían era el apropiado? Hasta el momento el Ingenuity no se ha separado más de 300 metros del Perseverance.
Sí.
Entonces, ¿en qué se basaron para este recorrido, para este alcance entre el helicóptero y el rover?
Courtney, you already told me that the average range of the communication link will be around 1 kilometer. We want to know if you have, when you were designing the link, the communication link, do you take into account that you are in another planet? I mean, another atmosphere, maybe, I don't know, maybe interference from metals on the ground or something. Do you take into account this situation?
Right. So yes, we did. So the atmosphere on Mars is about 1% of the density of the atmosphere on the Earth. So one thing you don't have, one thing you have on Earth is the 4/3 Earth, where the atmosphere will actually cause refraction of radio waves that go further than the geometric line of sight would have gone. But there's not enough atmosphere on Mars to really do that, so you don't get that effect. You really do have the line of sight, and once you go over the horizon, it's just gone. We looked at many other things. We studied the mobile radio work of Bullington from the 1950s through the 1970s, where he had studied all of these issues. What happens when mobile radio signals are refracted off of buildings or off of mountains or off of trees or go through different kinds of air. What happens when it's raining or when it's dry. He had studied all of these things, and we reviewed all of that and said, well, what are the cases like on Mars? And on Mars you have dust storms. And so we looked at the effect of dust on the signals, and it was negligible, according to theory. And, we basically ended up in a situation where it was just, if you have optical line of sight up to a kilometer or so, the link will work. And if you can't see it, if you can't physically see it, if you can't take a picture of the helicopter from the rover with the camera, because it's behind a rock or a ridge or something, then it probably won't work. It's just that simple.
Okay.
But we did look at all that pretty thoroughly and ruled out all of the all the things that were going to be problems. And the one thing I'd like to say was that we were looking at what happens with trees and vegetation and so forth, and I said, well, if we have radio interference due to trees and vegetations on Mars, we will not be the news. That will be the news, right?
Yeah. You're talking about vegetation on trees in Mars. Big news for everybody.
Right. So we haven't seen that, but if we did, that would be the news. They wouldn't be talking so much about the helicopter.
Okay, let me translate. Ricardo, ellos sí se apoyaron en muchos estudios que se habían hecho pues en el pasado con respecto a todos los factores ambientales que pueden afectar las radiocomunicaciones. Él me dice que la densidad de la atmósfera de Marte es 1% de la densidad de la atmósfera de la Tierra, pero que a pesar de todas esas variables y todo eso que se estudió, pues realmente no influye o no genera ningún impacto como tal en las comunicaciones de radio. Si nosotros miramos, por ejemplo, la velocidad de la luz, pues en nuestra atmósfera las ondas electromagnéticas igual viajan a la velocidad de la luz, igual que si están en el espacio, en el vacío absoluto. Entonces él me dice básicamente es eso, que no encuentran ninguna diferencia pues por estar en Marte.
Ok, muchas gracias, Mauricio. Sí, a mí me sorprendió este proyecto que usaron, por ejemplo, electrónica convencional de SparkFun y otros elementos que uno consigue pues, para los proyectos de investigación clásicos, ¿no? Normales. Fue
Sí.
interesante, o sea, no le querían meter mucho dinero a este proyecto y dijo, fue un gran resultado. Vamos algo comentó el ingeniero Duncan el tema de que había muchas tormentas de arena, pero entonces,
Ah, sí, correcto. Él habló de las tormentas de arena, pero aún así eso no afectaba para nada las comunicaciones, porque pues no son microondas, sino que están entrando en 900 MHz y no alcanza pues a ver tampoco ninguna interferencia o ninguna atenuación particular.
perfecto. Vamos con la siguiente pregunta. ¿Cómo es esa transmisión de imágenes de alta resolución desde el Ingenuity al Perseverance, o sea, del helicóptero al rover? ¿Cómo es? Porque pues les ha dado un gran resultado, porque como dije hace un momento, el proyecto solamente era una prueba, no le tenían mucha fe a que este helicóptero funcionara. Entonces resultó que ahora el Ingenuity con su cámara y de captura de imágenes de alta resolución se convirtió en una ayuda para trazar todos los caminos del Perseverance, algo que no tenían en cuenta, lo vinieron a descubrir ahorita que lo necesitaron, ya que el Ingenuity es capaz de discriminar el lecho rocoso frente a las dunas de arena para que no se vaya a varar, ¿sí? Asimismo, esas imágenes permiten tomar decisiones para evadir colinas que son muy elevadas, ¿sí?
Sí,
Entonces, ¿cómo esa transmisión? Porque cuando hablamos de una imagen de alta resolución es bastante información.
sí. Courtney, we understand that the helicopter is able to transmit high resolution images of the soil on Mars to the rover. How do you do to transmit those high those pictures with high resolution? We know that with that high resolution, we need a lot of bandwidth, a lot of data to be transmitted. How do you do that?
Oh, right. So, so to the radio system, all of that, everything is just data, and we handle a certain number of bits per second, and
Okay.
so that means that all the experimenters on the helicopter, such as the cameras and the people who monitor the motor operations and the various actuators and things, everyone gets a certain data budget for flight, and they negotiate this very actively, as you can imagine.
Yeah.
Um, I'm trying to remember. I think the high resolution pictures. So the cameras on the helicopter, they're similar to GoPros. In fact, they might be GoPros. They're just megapixel type small portable cameras that you'd have in a helmet or a webcam or something.
Ah, so the
But
camera is 4K too? 4K?
yes, yeah, they had the same restriction I did. They didn't have much mass, and so they had to do the lightest thing that they could do. And
Yeah.
there's two cameras on board. One points straight down, and that's used for navigation. What they do, they analyze the pictures, and they see the rocks and features going by as the helicopter flies, and they use that information as part of the control system. And as they see the rocks and features moving by, they can tell how the camera is pointed and so forth, and they know it's pointed straight down, and so they use that as part of the attitude control and the altitude control and the motion control. And then there's another camera that's a color camera called the Return to Earth camera, and it's pointed down at a 45-degree angle. I think the picture we're looking at now is one from that, where you can kind of see out more toward the horizon in some cases when the helicopter tilts back a little bit. But it was thought that that would give the most information. And so what they do, they, in a nutshell, so the system, the radio system will move about 80,000 bits per second, about 80 kilobits per second when it's in operation. And what they do during flight, they have certain parameters they want to look at, and that uses up 55,000 bits per second of bandwidth, and they just, and that's all they do during the flight. What they do, they have a flight, and then they land someplace, and then they rest for a while, they let the battery recover, and then later on they'll have a telecom session of 1 or 2 hours, and this might even be over the next several days, but after the flight's over, there'll be a telecom session of about a half an hour, and then the next day there'll be a telecom session only for 2 or 3 hours, and so that's how they get the large number of bits back. And you know, once at 80 kilobits per second, once all the data gets off of the helicopter back into the rover, then it's all rover data, and it all comes back to Earth in the same ways that all the other rover data comes back to Earth. To them, we're just another experiment that has some data.
Okay, let me translate. Ricardo, lo que tú habías explicado es lo mismo que él nos está contando acá. Ellos tienen cámaras, tienen 2 cámaras y son parecidas a las GoPro, a las que conocemos aquí, pues, pero de alta resolución, o sea, 4K. Tienen una mirando hacia abajo y una dedicada a la navegación, lo que tú decías. Entonces el helicóptero está mirando el terreno adelante y él puede, con su software, pues puede discernir dónde hay piedras, dónde hay laderas, todo lo que tú decías, para mandarle esa información al rover. Entonces él dice que el helicóptero toma los datos y después para, o sea, aterriza y tiene una sesión exclusiva de telecomunicaciones para mandar todos esos datos, pero es a una velocidad baja. Él dice que 8.000 kilobits por segundo. Entonces se demora 1 o 2 horas en enviar todos esos datos al rover para que ya el rover los procese y ya mande esa información ya directamente con el link a la Tierra.
Perfecto, listo. No, sí sabía el tema del lapso de tiempo para la transmisión de estos datos. Es que siempre alta calidad, transmitirla rápido es complicado, ¿no?
Claro.
Vamos con el siguiente tema. Permítanme avanzar acá en diapositivas, pero acá, figura 4. La 4. No sé si estoy... listo, sí. En el diseño del sistema de transmisión de datos del Ingenuity, ¿qué alternativas se tienen si se presenta una interferencia? ¿Sí? Por ejemplo, en el vuelo 17, hace poco, creo que fue la semana pasada, se tuvo un apantallamiento por parte de una colina pequeña de 4 metros de altura que se llama BRAS. Los enlaces entre las antenas del rover y el helicóptero son del tipo LOS y hubo un corto de comunicación, o sea, se separó la comunicación.
Sí.
Sí, se sabe que pues una vez se pierde la comunicación, el Ingenuity aterriza y se apaga. Pero, bueno, ¿qué más hay con respecto a este tipo de interferencias en caso de que se presenten?
Courtney, Ricardo is talking about event that happens with an interference with a small hill called brass, and if you don't have a complete line of sight between the helicopter and the rover, and for some reason the link is broken, what will happen in that way? Is there any way to restart the transmission, or how you handle that situation if you lost communication for an obstacle, for example?
Right. So this was a thing that we wanted to avoid, but we knew that it wasn't always going to be avoidable. And in fact, the incident you're talking about here is one where the helicopter went off and landed basically at the edge or slightly beyond the edge of where it would work. And so they basically lost control for a few days until the situation improves. And so the way this is dealt with is that the helicopter can operate totally autonomously.
Okay.
And once you so starting from the time that it's deployed, when it's deployed, it stays asleep, and 2 hours after it's deployed, it knows that it's deployed because it's disconnected from the rover systems. Then 2 hours later, it wakes up and turns on the radio and listens for beacons from the rover. And once you've established communication the first time, so this was a critical thing the very first day, once you've established communication the very first time, then ever after that, the helicopter turns itself on every 12 hours and listens for beacons. And if it doesn't hear anything in about 15 minutes, it just turns itself off. And then 12 hours later, it'll come back on again. And we know, based on the clock setting on the helicopter, when it's supposed to be on. And so when they want to talk to it, they'll turn on the rover side and they will establish communication. And when they don't, they just don't. And so the rover sits there, it comes on and listens every 12 hours. Now, when you're out of sight, it won't hear anything even if you are trying. And so what needs to happen is that in the case we're talking about here,
Yeah.
they eventually drove the rover to a different location, either to reestablish communication or for some other reason. And then they were not blocked. And then the next time a communication attempt came up, it succeeded, and then you were going again. Now, the longest time this ever happened was over solar conjunction, which occurred 3 or 4 weeks in October. And they basically, at solar conjunction, Mars, as viewed from the Earth, is only 1 or 2 degrees away from the sun. And so they stand down all the missions, the rovers and the orbiters and the helicopter, they stand everyone down for 2 or 3 weeks. And so it was very interesting to us to see what would happen after solar conjunction when everyone was turned back on and come back into communication. Would the helicopter still be there after it hadn't heard from the base station in 2 or 3 weeks? And they did recover it early, late in October after conjunction was over. They did recover it, and they have continued. They've continued. So yeah, that's the way we deal with it. We just know that the thing is going to try every 12 hours. And and I'll say one more thing about that. The reason it's every 12 hours instead of every 24 hours is because you don't know that a system on the helicopter might fail. One of the big concerns we had was that, for instance, the battery might run all the way down. Yeah. And then the next day when the sun came up and the solar panel was illuminated, it would come back on. But at that point, it would come on cold, and this clock would restart, and the 12 hours would start from that point instead of from the point where we last set it. And so in the case where something like that had occurred, where there'd been a malfunction, what you would do, you would have the rover come on every 15 minutes throughout a 12-hour period and just try to find the one when the helicopter did come on. And once you'd established communication, then it would know what to do. Then things are reestablished. But up until that point, you're just hunting every 15 minutes to see if you can find when the 12-hour timer was reset to.
Okay. Entonces, él dice que el helicóptero es autónomo, ¿cierto? Él tiene como su propia inteligencia y el sistema está diseñado, Ricardo, para si él pierde la comunicación, pues él aterriza y se queda ahí donde está y cada 12 horas él trata de llamar al rover. En caso puede que se haya perdido, lo que le entiendo a él es que en caso que se haya perdido la comunicación, cada 12 horas él se activa y trata de llamar al rover para establecer una comunicación. Si en esos lapsos de tratar de establecer la comunicación. No se pueden comunicar porque hay un obstáculo o porque aterrizó de pronto lo que tú decías, de pronto ya después de la montaña. Entonces lo que tratan en tierra es de mover el rover para evitar, pues, para hacerle el quite al obstáculo y poder tener comunicación. Él contaba un evento que hubo alrededor de 4 semanas en octubre. eh, no la entendí muy bien, pero creo que es como la alineación pues, del Sol con la Tierra y Marte, en donde se hacía muy difícil la comunicación y entonces tenían mucha expectativa porque iban a quedar como a ciegas. Y entonces tenían expectativa de cuando eso pasara, cómo iban a estar tanto el helicóptero como el rover, pero todo estaba en su sitio y todo, o sea, el protocolo está diseñado para manejar esas situaciones.
Perfecto, muchas gracias, Mauricio. Bueno, vamos avanzando rápido a los otros temas. Aquí prácticamente voy a meter dos preguntas, pues no están relacionadas con la anterior, pero son prácticamente puntuales. Es en cuanto a interferencias, ¿sí? ¿Qué otros elementos pueden generarnos fallas de interferencia en la comunicación? Entendemos que eso tiene un reactor, el MMRTG, que es nuclear, creo que eso puede generar interferencias, la misma estructura, en fin. Y lo otro es, ¿por qué la pérdida del enlace puede llegar a ser grave en el momento en que está aterrizando el Ingenuity? Pues según los informes que han dado el JPL.
Courtney, we're talking about interference between the communication and the communication link between the rover and the helicopter. We suppose that we don't have any kind of interference, I mean electromagnetic interference in Mars, because we don't have any radio station, nothing transmitting over there. But we're talking about the rover itself, the systems inside the rover can make another maybe some interference with the communication link?
Yes, there could be. So in general, what you do, yes, all the possible interference, electromagnetic interference you brought to Mars with you, either on the rover or on the helicopter. So there's two answers to this. One is that on the helicopter, we didn't have the mass to do any kind of shielding or any mitigation of interference. So there was a concern throughout development that, for instance, when the thing was flying, the motor, the motors they're using switched power at 10 or 20 kilohertz.
Yes.
And they're switching several amps. They're switching 10 or 15 amps. And all this is right within centimeters of the 900 megahertz antenna. So there was concern that all that electrical noise might block reception, and we therefore implemented a mode of operation that didn't require the receiver to be working. So during flight, it could just be transmit only, and then we didn't have to receive anything back from the rover. Now they haven't actually used that mode, and it turns out that there wasn't the interference that we feared that there might be.
Yeah.
But that's we just weren't able to test it, and there wouldn't have been a good way to test it on Earth anyway. So we just had to allow for that. Now the other case is, of course, everything on the rover itself is all the instruments and all the subsystems are electronic, and they all have their power supplies and their switchers and different things that emit energy. And
Right.
so every subsystem on the mission is required to be radio quiet in the frequencies that we're trying to use, and they're also required to themselves tolerate our transmission. So when we transmit at 900 megahertz with a watt, that can't upset anybody else. If that's going to upset your camera or some other instrument, and you know how this happens, right? Sometimes you transmit on your radio and your computer screen fouls up or something. So that's not allowed to happen. And so if that happens, then you have to work on your instrument to make it more resistant to that. And your instrument is not allowed to radiate more than we can stand. And we discussed this quite a lot. A lot of the work was to try to mitigate all those effects and to make sure that it would work. But in the end, there just wasn't any way to absolutely verify it until we got to Mars and saw it work. Now, it's interesting, this picture you're looking at, it shows a line of sight through the radiothermal generator, which is our worst direction. We have an antenna up there on the upper side of the picture.
Yes.
And if the line of sight goes through the RTG, that has 20 or 30 dB of extra loss over a clear shot. And we did, in fact, right after deployment, when they drove away in that direction so that we were right behind. And it did have, it was 20 or 30 dB lower than we would have expected for the 20 or 30 meter range. And so the radio did work because we were so close, but that is a problem. And if they park with that line of sight that you see there at a kilometer distance, it just won't work. There's just too much loss in that direction. So they would have to rotate the rover around a little bit or something to get a clearer shot.
So you have experienced degradation of the communications link, the quality of the link because of that?
Yes, and when we say degradation, so these are digital packets that are they're protected with spread spectrum. The coding gain is 11 or 12 dB due to the spectral spreading. But
like the signal to noise radio.
Right.
Okay.
But and we did extensive lab testing to see how far down they would go. And what happens is that when you get down to where the received signal is about minus 95 dBm, you start to drop packets. Okay. And over the next 5 dB, when you get down to minus 100, you're dropping most of the packets. And so it really falls off very quickly. Okay. And then when you get down to minus 105, you can't see anything at all. And so between minus 95 and minus 105, it just plain stops working. And that's what we mean by degradation. So the thing is, if a packet gets through, it has the checksum has worked, and all of the protocol. The fact that it got through means that it's correct, nearly certainly. Yeah. And if it's not correct, then it just doesn't get through. And so the degradation is all dropped data. And then someone at a higher level has to deal with that. Yeah. Right. So someone at a higher level has to deal with, if you think data was lost, then you schedule a time tomorrow under better circumstances to try to retransmit it then. That's right.
Okay, let me translate. Ricardo, sí, pues el tema de la interferencia era algo que ellos tenían muy en cuenta, que se podía presentar, realmente no por las condiciones externas, como hablamos ahorita, sino por los mismos sistemas y los transmisores también y los equipos que tiene el rover como tal. Digamos en el helicóptero, la preocupación era por los motores, como ellos trabajan, son motores eléctricos que trabajan switchados y con muchos amperes, pues eso genera ruido. Entonces ellos tenían, de ese ruido de switcheo de baja frecuencia de kilohertz, pues era como una preocupación, pero no han tenido problema como tal con el helicóptero. Con el rover, la foto que tú estás mostrando, él me dice que hay una parte del rover que entiendo que es arriba, como ahí donde estás viendo el carro, como arriba a la izquierda, hay una parte que es la parte térmica, un sistema térmico.
El motor.
Eso. El motor. Si el transmisor, o sea, la antena de los 900 MHz para hablar con el helicóptero, se alinean esa parte del rover con el helicóptero, se pierde la señal por la interferencia que genera. Entonces, Courtney me dice que el link para que los paquetes entren y sean procesados de forma normal está en un rango de menos 95 a menos 105 dBm, que es la intensidad de señal de recepción. Él me dice que cuando ya baja más de eso, se empiezan a perder los paquetes. Entonces los paquetes, como esto es un protocolo inteligente, la información no es que se pierda, sino que al no llegar y no recibir el acuse de recibo, pues tienen que volverlos a mandar. Entonces ellos van a tomar más tiempo, porque entonces todo eso que no llegó tienen que volverlo a enviar. No es una información que simplemente se envió y se perdió, sino que tienen que volverlo a enviar. Entonces van a requerir de más tiempo, básicamente.
Correcto. Vamos avanzando, que habíamos dicho 45, pero ya vamos con más tiempo, no hay problema. La siguiente pregunta es más con la transmisión de datos hasta el planeta Tierra. Courtney ya nos había comentado algo, el ingeniero, pero vamos a hacer la pregunta puntual. Si se genera, bueno, nuevamente algún problema, ¿cuánto tiempo se demora en pasar la información desde el Ingenuity a la Tierra, o sea, a nuestro planeta? Se entiende que pasa por el Perseverance, luego por el radio UHF Electra Mars, del Mars Reconnaissance Orbiter, y esta información se debe captar en el Deep Space Network. Y yo le había hecho ya esta consulta, sería de pronto que nos la ampliara en esos términos. Hago un paréntesis, el propio MRO, Mars Reconnaissance Orbiter, que es la sonda que está volando, ¿sí? Se comunica al suelo en una banda X de 7.2 GHz hacia adelante y hacia atrás en 8.4 GHz. Esa era una información que previamente ya me ha dado el ingeniero. ¿Sí? Existe un método pues, que él nos comentó, pero prácticamente la pregunta es que si nos puede ampliar cómo es ese proceso de la transmisión de datos al planeta Tierra. Y él me comentó que usan una aplicación que es el NASA Space Time. ¿Listo?
El NASA.
Space Time, que él me dice que la consigue en iOS, pero yo estoy investigando, también se consigue en Android. Entonces, la idea es, la pregunta es, ¿cómo es este procedimiento del envío de información de todo lo que está pasando hasta el planeta Tierra? ¿Por dónde pasa, qué aplicaciones utilizan para saber cómo está todo? Ya aquí
Okay.
en Tierra.
Okay, Courtney, what is the path that the signals that are originated in the Ingenuity? What is the path to send that information direct to the Earth, to the ground station here on Earth?
Right. So on Mars, Ingenuity only talks to Perseverance on 900 megahertz. That's it. There is no direct-to-Earth link from the helicopter.
Oh yeah, that would be impossible. Yeah.
Right. I mean, you know, I often wondered if someone with a huge dish might listen for it or something. There might be detectability, but it would not be a communication path. The protocol wouldn't support the long delays, for instance. So the whole interaction is with Perseverance, and Perseverance has the data management of the helicopter and all the other experiments on board, and they have a very similar negotiation where all the investigators of all the experiments get some data that comes back to Earth, and there are two ways that can happen. By far, the most common way is through the three orbiters at Mars. Right now, the Mars Reconnaissance Orbiter, the MAVEN Orbiter, and the Trace Gas Orbiter. All three of them have electro radios that we built on them, and they interact with Perseverance, and in fact all the other missions on Mars too, with the Curiosity, which is another part of Mars, and the other missions that are active. Yeah. Every time they fly over, they have a comm session in which they communicate at 1 or 2 megabits per second for 15 or 20 minutes. And they play a game of trying to see how much data, you know, a gigabit or a gigabit and a half every day return to Earth from there. So this UHF session it's in full duplex from orbit to the surface. And the surface transmits at I want to say 401.5 megahertz, and the orbiter transmits at 437 megahertz, and they interact with each other. And most of this is 2 megabits per second at 401.5 megahertz coming up to the orbiter, and then the data is all stored in a computer on the orbiter until the next session with the Earth. And on Mars Reconnaissance Orbiter, which is the biggest and best of them, there's a 3-meter dish, and it points back toward the DSN, and they can get, depending on the distance between the planets, they can get 100 or 200 or 500 kilobits per second back to the Earth. And so they'll have these long comm sessions, and all the data streams back to the Earth, and then it goes through our own networks, and a few minutes later we start to see it accumulate down here. Now, there's another way that you can talk to Perseverance. There's a so-called direct-to-Earth link on X-band, where Perseverance has a small, let's see, I don't remember how big it is, but it's
parabolic dish?
It's not a parabola. It's just it's a flat panel dish, and it's like, I think it's 1 foot. I think it's like 30 centimeters in size, but you might check that. And they point that at Earth, and they are able to get not quite a kilobit per second. The time that we did this, the return to Earth direct from Perseverance was 800 bits per second. So they don't like to use that except when they have real-time needs. And the time that we had this was when we were deploying the helicopter, and we wanted to see immediately if anything had happened, and to make decisions quickly if necessary. You know, when you're going through through the orbiters, the whole cadence is about a day. All this relaying takes about a day, and then you spend the night on Mars planning the next day on, whatever time that is on Earth, you spend that time planning the next day, and then an uplink happens. And so any interaction you have takes about a day. If you want to look at something different, you have to get into the next command sequence, and that's tomorrow at the earliest. So if you want to look at it near real time, only 20 minutes away, which is the light time, then you have to do this direct thing, but it's so slow that you can't see very much. And so nothing unusual happened on deployment day, and that was nice. And things just went as they should have, and we saw the helicopter wake up after the 2 hours and start talking, and we got the first thumbnail pictures. That means very low resolution first pictures that are taken, and then later on they get the full resolution at their leisure over a much longer pass. So there's the two ways, and both MRO and Perseverance, when they're talked back to Earth, that's on X-band at 7.2 gigahertz.
Okay.
They receive from Earth at 8.4 gigahertz, but they transmit to Earth at 7.2 gigahertz.
Ok. Ricardo, entonces hay dos formas de comunicar la información desde el Perseverance. O sea, del Ingenuity al Perseverance solo hay un link, que es el que hablamos al principio, de 900 MHz. Solo ellos dos hablan y ahí no hay nada más. Entre el Perseverance, para mandar esa información a la Tierra, hay dos formas. Tú lo mencionabas ahorita. Una forma es por los orbitadores que hay, los 3 orbitadores que hay sobre Marte, alrededor de Marte. Él hace una comunicación, el Perseverance se comunica en la banda en 400 MHz con esos orbitadores, pasa los datos, esos datos se almacenan en las computadoras de los orbitadores y ya después hacen una sesión de comunicación entre la Tierra y los orbitadores en la banda X, en 7.26 gigas. Y hay otra forma directa para comunicar el Perseverance con la Tierra, que también es con la banda X, y él me dice que el rover tiene una antena panel donde se pueden comunicar, pero como en última instancia, porque ya la velocidad de transmisión es muy bajita, son 800 bits por segundo, y eso pues para mandar bastante información, eso se demora una eternidad. Entonces, él me dice que como las comunicaciones son prolongadas y demoradas, ellos se toman un día para programar, digamos, lo que va a hacer el rover el día siguiente. Entonces, en un día él manda toda la información y ellos, mientras van mandando la información, ellos programan lo que va a hacer el rover y ya lo envían en esas sesiones. Como eso está tan lejos y los enlaces son tan demorados, pues entonces no es que se esté viendo pues en tiempo real lo que está mandando en ese caso el Ingenuity, sino que pues toma tiempo y recibir todos esos paquetes de datos pues también toma mucho tiempo.
Correcto, Mauricio, muchas gracias. Sí, una de las tantas temas o bloques, bloques no, sino problemáticas a las que se enfrenta uno con estas misiones, ¿no? Las comunicaciones a estas distancias tan grandes. Listo. Vamos a avanzar a otro tema acá. Listo. Creo que el ingeniero lo comentó, el ingeniero Courtney, pero me gustaría profundizar más con esta simple pregunta, ¿no? Basada en las figuras que vemos acá en la imagen, ¿cómo se diseñaron las antenas? Que creo que lo fundamental en todo lo que es comunicaciones, yo creo no, es lo fundamental en comunicaciones. ¿Cómo fue ese diseño de antenas para saber que precisamente esas antenas, esos diseños iban a funcionar?
Pues él nos comentó al inicio, Ricardo, que el helicóptero tiene simplemente una antena cuarto de onda omnidireccional, vertical,
Ok,
y que es compatible con la tecnología que están utilizando, que es la Zigbee, ¿sí?
ok.
Entonces es simplemente una antenita de cuarto de onda vertical, que es la misma que tiene el helicóptero y tiene el rover, pero solo para el link entre ellos dos.
Perfecto, sí. El alambrito que llaman, sí, el pequeñito.
Eso sí.
Bueno, ese no, entonces no nos detengamos tanto ahí, pasemos a la otra parte.
Yo
Eh,
quiero preguntarle a él sobre el tema de las baterías. ¿Qué baterías tienen y si tienen paneles solares?
Dale, dale.
Courtney, we're taking a look here at the helicopter picture of the helicopter. We are wondering, are you using batteries on the helicopter, or you're using solar panels, or what is the? How are you giving power to the radio?
Right. So everything on the helicopter is powered by 6 batteries um, that are in the center of the little helicopter, the little square helicopter assembly at the bottom. And
Uh-huh.
they're not double A's, but they're about the size of double A's. And they're a type of battery that was chosen because they can stand a very high discharge rate. When the helicopter flies, it takes about 300 watts to operate, and so that really, let's see, it's a 21 volt. All the batteries are in series. It's 21 volt in series, so it's about 15 amps, 15 to 20 amps when they're taking off, and 15 amps when they're flying, and so they have to do that for a minute or two. So the batteries have to be able to do that. The radio itself, it only takes let's see, it only takes about 700 milliamps
Yeah.
key down transmit, and so that's not anything like that's not anything
Motors.
like
Yes.
the big load of the motors. And
Yeah.
so we can run for hours and hours. And yes, the batteries are topped off and recharged by solar panel, which is right underneath the antenna there. We use the solar panel as a ground plane, and it's a kind of a complicated situation, but the solar panel charges the batteries at full illumination. It's about 1/4 of an amp, and you know, as the sun goes up and down, it's less than that most of the time. But that allows us to keep the batteries topped off from day to day, and then they just budget for, you know, how long can they fly and how often can they fly and how often can they use the radio. But the radio is not a big it's
Yeah,
not the big
it's
consumer
not
of
a
the
big deal.
batteries. Right. Yeah.
Okay. Ricardo, sí, lo que me imaginé, ellos tienen un banco de baterías porque lo que decía Connie es cierto, o sea, el consumo del helicóptero pues son los motores, ¿cierto? Como
Correcto.
cualquier dron. El link de radio realmente consume muy poco, que son como 700 miliamperios. Pero pues los motores sí, las baterías son de 20 voltios y consume aproximadamente 15 a 20 amperios cuando está volando. Y más teniendo en cuenta, me imagino que pues la atmósfera tan poco densa, pues necesita mucho más revoluciones el motor para subir. Entonces tienen unas baterías especiales parecidas a las AA y tienen panel solar para cargarlas. Un panel solar que yo creo que se ve ahí en la foto que tú mostraste del helicóptero, ahí en la parte de arriba, esa parte plana, esa es el panel solar para
Correcto.
cargar ahí las baterías.
Correcto, y de ahí le sale la antenita. No, muchas gracias, Mauricio. Entonces, devolvámonos acá. Vámonos a ahorita, bueno, sigamos con esta parte. Esta es la estación base del helicóptero, ¿sí? Que está instalada en el Perseverance. ¿Será que nos puede dar como una información de cómo, qué tiene adentro, de lo que podemos ver ahí a simple vista? ¿Sí? Que pues la función de radio experimental es como más entender la parte de la electrónica que lleva. Sí, de pronto si el ingeniero Cornell nos puede explicar lo que vemos en la imagen ahí, qué es, cómo está compuesto.
Connie, can you explain to us, please, what we're looking in this picture? What is that?
Yeah, this I haven't actually seen this before, but this looks like the part of the base station that's mounted on the rover, and what you see. So what we did, we made a symmetrical system. For instance, for the telecom system and for the computer system that it talks to, it's the same system on both sides. There's a telecom board on the helicopter that's nearly identical to the one on the rover, and that is underneath the assembly you see here. It was they're stacked and folded, and I think the telecom board is on the bottom. And what you're looking at here, of course, is the top right before they closed it out. So this is other subassemblies that are not related to the comm system. You know, that box there looks like. Let me see. No, it looks like it has coaxes coming out of it, but that's not part of the comm system. That's part of something else that's involved in the base station operations.
Uh-huh. Sí, Ricardo, él dice que si es hace parte del base station para el helicóptero, pero que todo eso que estamos viendo ahí no es propiamente, o sea que hay más cosas y más sistemas. Probablemente alguno de los módulos pequeños sea el transmisor. Él dice que son simétricos, son exactamente igual al mismo módulo el que tiene tanto el Perseverance como el helicóptero, pero ahí pues se ven muchas más cosas porque se ven varios cables coaxiales y varias unidades.
Correcto. No, el tema de la curiosidad, ¿no? De saber qué más tiene ese equipo. Bueno, que el tiempo apremia, pasemos a otra parte. Ya permítanme un momentico. Listo. Bueno. Esto es para preguntarle a ingeniero si él conoce algo sobre el proyecto Mars Science Helicopter. Por ejemplo, si trae mejoras en el tema de comunicaciones, si todo el equipo del ingeniero Courtney va a volver a participar en el concepto de él, qué se puede mejorar en comunicaciones con lo aprendido ya en el Ingenuity.
¿Y ese proyecto es de ellos o eso es aparte?
Supuestamente es el futuro, o sea, vemos el Ingenuity, que es el pequeñito aquí a mano derecha.
Sí.
El grande es el Mars Science Helicopter, o sea, va a ser la evolución del Ingenuity. Entonces, para ese no sé si lo va a coger el JPL o si la pregunta como tal es si el equipo del ingeniero Courtney va a trabajar en este nuevo dron. ¿Qué mejoras le podría poner basado en la experiencia que tuvieron con el Ingenuity y generalidades sobre este proyecto?
Courtney, do you know something about this Mars Science Helicopter, this project?
Right. So this is the so the idea of the Mars helicopter. It's a technology demonstration to see whether it's possible and whether it's worth having a vehicle that can fly on Mars. And I think we were all surprised. Not only we weren't surprised that it was possible, because we'd studied this for years. We'd had aerodynamics people look at blades and different things, and we knew that it would be possible. But we didn't know how valuable it would be. But it's turned out, even on this mission, that we have been able to go off and look at places that the rover can't go to, and get useful data both for planning and for science. And the idea now, you know, in the same way that in 1997 we put a rover down on Mars for the first time, and very similar, to see if it was worth doing. And now we've sent several rovers to Mars to drive around and look at interesting places and dig up certain kinds of rocks and certain kinds of soils and different things. So now we're thinking that you know, the next step would be to send a full-up mission of its own. And so what you're looking at here is the current version of planning for what would be a standalone mission, or a mission all unto itself, of Mars Science Helicopter. And they would send this to some location that was particularly not suitable for a rover, or not suitable for a lander that doesn't move. But, you know, it might be a rough area that that you couldn't drive around, but you could fly around. And the nice thing about this, so I was so I retired and left JPL in July. But I was involved with talking to the Mars Science Helicopter people. They're designing a mission, and it currently, the thinking is that it might go in the 2028 Earth to Mars launch opportunity. And it would be on its own. And the nice thing for me was that this is a much larger helicopter, and it has you know, it has more room for experiments, and we could probably have 100-gram radio on here instead of a 10-gram radio, and so that would that would be very nice. And one of the things we certainly want to do is connect the science helicopter directly to the Mars network, so that this helicopter would talk directly to MRO and the other orbiters, so that they wouldn't be tied down to wherever some nearby rover wanted to go. If they're talking to the rover, to the orbiters, they can go anywhere on Mars, and they can get passes with the orbiters like anyone else on Mars, and they can get hundreds or millions of bits per second just directly to Earth, like everyone else at Mars does. So that would be nice for us, and that was the thing that I was advocating for towards the end.
Okay. Sí, Ricardo, pues yo no lo conocía. Ese proyecto es como la mejora del Ingenuity, y él dice pues que lo están presupuestando a ver si lo pueden llevar en el posible en el 2028. Posiblemente van a mandar pues otra misión a Marte, y obviamente pues este helicóptero tiene mejoras, empezando por el tamaño, por el diseño de las hélices. Mira que tiene mucho más rotores, mira que tiene mucho más autonomía. Él dice que tiene más capacidad, pues obviamente, de llevar experimentos, equipos pues para experimentar, me imagino.
Payload, carga útil.
Sí, tiene, digamos, en la parte de comunicaciones, la ventaja que va a tener es que él no va a tener que comunicarse con el rover en la superficie, sino que se va a poder comunicar directamente con los orbitadores. Entonces eso le va a permitir poder tener un link más rápido y poder, digamos, poderse mover de forma más autónoma, porque no va a depender de la comunicación que tenga con el rover abajo, sino con los orbitadores siempre va a tener contacto. Entonces va a mejorar tanto la comunicación como la habilidad pues de desplazarse en el planeta.
Ok, excelente. Vamos ya dentro de las últimas preguntas a volvernos a la parte ya del grupo, de equipo. Vemos en la primera diapositiva, qué pena es que no la puedo maximizar porque no me las deja mover, no sé qué pasa con el Google, con el Meet, pero vemos que hay un equipo grande, ¿sí? que formó este proyecto. Está tanto, obviamente, liderando el ingeniero Courtney, pero también aparece Matt Chase, Kilo, Foxtrot 7, Whiskey, Papa Golf, que es el encargado de la interfaz del software. Está Jorge González, que sería interesante conocerlo, que es Kilo India 6 Bravo, Juliet Bravo, encargado del test bed. Sería interesante saber el test bed de qué se trata. Peter Aylott es Kilo November 6 Golf Lima Oscar, parte de telecomunicaciones. Está Eric Archer, que es November 6 Charlie Victor, fundador, ¿sí? Hay un equipo de prueba de campo, Josh Miller, que es Kilo Bravo 3 Unión y Unión Sierra. Está Manu de Crozas, que es Kilo Foxtrot 5 Quebec, Kilo, perdón, Oscar Eco. Está Dave Bell, que es Alpha Hotel 6 Hotel Oscar. Sí, bueno, tenemos todos estos radioaficionados, entre otras personas que aparecen. ¿Cómo reunió el ingeniero todo este equipo?
Courtney, Ricardo would like to know, how do you work? How do you talk with all these ham radio operators that we are seeing here in this slide? And how do you choose everybody to work in this project?
Well, it's interesting that a lot of people who work in radio at JPL are hams, yes, amateur radio operators, and the ones who aren't, we're often working on to to get them licensed, because they should be. So a couple of examples here. Peter Eilot, KN6GLO, has been the telecom expert for everything that's going on at Mars for 20 years at least. Mm-hmm. But he, and we've been working on him for all that time to get him licensed. And so finally, only a couple of years ago, he went out and, he realized he's approaching retirement and he wants something to do in retirement. But he also knows that, all the hams that he knows are pretty knowledgeable people about this sort of thing. And so he respects the hobby, and he wanted to be part of it. And so but he's just recently licensed. And I thought that was interesting that he would come along at this point. Yeah. I have to mention Dave Bell is my AH6HO is my supervisor, and he is really a sharp telecommunication engineer also, and he just had both technical and political insights into this that were invaluable. And a person that we're still working with who ought to be mentioned, the antenna designer, is Nasser Shahat, who is he's a French national who works at JPL and has for about 5 years now, and he is so busy designing antennas for this and other missions. He's designing an antenna to go to Europa and land on Europa and be in the cold and radiation environment, and and talk back to Earth and so forth. He's a brilliant antenna designer. He knows how to use all the modern tools, but we have not been able to get him enough spare time on a weekend or something to get his license yet.
To get a license, yeah.
So he should be on there, and he will be someday, but but is not yet.
Okay, sí, Ricardo, mira, pues obviamente toda esta gente son profesionales, son ingenieros con mucha experiencia, y él cuenta que la mayoría de ellos que pues tienen su licencia apenas la sacaron hace poco, porque de cierta forma también es requisito para la operación que están haciendo, pero son ingenieros que llevan muchos años trabajando en el JPL, ¿sí? Y que pues que también les gusta, y que él decía, por ejemplo, el caso de uno en particular, pues que está próximo ya a retirarse, a jubilarse, y que también pues le encanta esto y que quiere también el hobby, y se licenció pues hace muy poco. Entonces básicamente gente que ha trabajado con ellos en el JPL durante muchos años, y que se han licenciado como radioaficionados.
Perfecto, muchas gracias, Mauricio. Bueno, ya la última pregunta va como,
Last
sí,
question.
los grupos como nosotros queremos participar en estos proyectos, ¿qué debemos hacer?
Okay, Courtney, the last question. Talking about the groups, the ham radio groups like us, how can we make part or participate in those kind of projects? Is possible?
You know, I think it is possible in the upcoming era. You know, the Mars helicopter has been kind of an eye opener for, you know, as I said at the very beginning, we build big radios that go to deep space and survive hostile environments, but we're not really used to these small single purpose things. But a lot of people have been coming to us asking how we did this. They're designing, for instance, little swarms of rovers that would go to the moon and drive around in a small area, a few hectares or maybe a square kilometer, and you know, they would all talk to each other, and they would have to use a radio paradigm similar to what we've done here. It would have to be some kind of mesh network and some kind of, you know, hopefully some kind of fairly standard protocol that they wouldn't have to do a whole lot of developmental work to start using. And, you know, it occurs to me that in preparation for things like that, ham radio groups could do similar things on Earth, and you know, you could set up a little network of rovers or even fixed stations, and in fact we've had a couple of projects that kind of did this kind of as a training exercise for students. But ham radio operators could set up something like this and learn some things about how it works and learn what some of the issues are, and they could publish papers.
Yeah.
And then we would read the papers and you know that and perhaps consult with or at least use the information. I know that so long before I was at JPL, I was a volunteer at AMSAT North America.
Oh, nice.
And I wrote a paper in 1986 about you know, Earth orbiting satellite telecommunication passes and the kind of antennas you would need and the kind of passes you would expect for certain orbits. And it was very interesting that many years later, up in the 2000s, one of the managers at JPL, he said that he had gotten you know, he had gotten a PhD in communication science and about Earth orbiting satellites and so forth. And one of his main resources had been this paper that I'd written for amateur radio back in 1986. And you know, he had really digested that. And so, you know, amateurs have things to contribute. We can do tests, and you know, we can do tests on Earth, and we can talk about the things we learn, and that is helpful to the professionals. But I would also say that in the current era, there are a lot of little startups and nonprofits, such as the Open Research Institute in San Diego, and other places that are doing space-based planning and planning to do operations and development in that area. And this is of, by, and for amateur radio operators. And so there is, even in space itself, or, you know, these startup companies that want to do something like send little groups of rovers to the moon and things like that, they will need telecom experts, and hams just basically show up already understanding how these things all work, and they could be helpful. So you could actually get involved with these small outfits that are planning specialized experiments like that. I think there's going to be a lot of opportunity, and I would just watch the newspapers for what's going on and see what you can get in on.
That's a pretty nice recommendation for us, Courtney. Let me translate. Ricardo, él dice que, por lo que hablamos al principio, que hay mucha posibilidad pues, de que los grupos de radioaficionados como el nuestro puedan participar en un futuro en este tipo de proyectos. Una recomendación importante que da él es empezar a hacer experimentos y pruebas aquí, ¿cierto? Tratar como de replicar ese tipo de tecnologías, como la que nos explicó él hoy, y empezar a hacer experimentos que en un futuro es muy probable, ellos siempre van a seguir necesitando para futuras misiones, pues, ayuda de radioaficionados. Entonces es como una forma de nosotros que no estamos involucrados directamente con ellos, pues empezar a hacer nuestras propias pruebas, nuestros propios ensayos y acercarnos en un futuro de pronto a poder colaborar con estos proyectos grandes.
Perfecto, correcto, así lo vamos a hacer. Bueno, aquí ya activamos a cada momento. Cámara. Sí, sí, ok. Qué pena, salió ahí toda la... Perdón. Sí, disculpa. Ok, ya, para terminar en cámara. No, ya aquí para despedirnos, pues agradecerle todo el tiempo que nos ha dedicado, ingeniero Courtney. Para nosotros es un placer, pues, poder tenerlo aquí con nosotros. Mm, es información, pues, de punta de un proyecto que pues, se ve muy lejano en otro planeta, pero que nos enseña bastante tecnología, ¿no? En las comunicaciones, para lo que está enfocado esta conferencia. Entonces, no me queda más sino decirle que estamos muy agradecidos, que esperamos contar con él tanto en Radio Experimental Mundial, que nos encuentras en Facebook, y más adelante tratar otros temas.
Courtney, we would like to thank you very much for all your time, for all the knowledge you have shared with us. It's been a pleasure for us to have to receive that knowledge from you, your experience. We love those subjects. We love to experiment. We have Facebook groups, and we would like to keep in contact with you. And we will be watching the progress of this spectacular mission. And we're very pleased to hear you and to receive the valuable information for us. Thank you very much.
Okay, well, it's been a pleasure to join you today. I hope that some of what I've said has been interesting and informative for you. And I would say good luck with all your future endeavors. And when we started with the helicopter, it was supposed to be a 30-day mission, and the darn thing is still running after what is it, 7 or 8 months now.
Oh,
so we've been pretty lucky, but it's also I guess the environment wasn't as hostile as we expected. so anyway, I'm glad that it's been an inspiration to everybody, and I hope that
pretty much.
I hope you guys are able to do stuff as a result. And please contact me anytime. Be happy to answer your emails or whatever.
Thank you, Courtney. Thank you very much.
Okay.
Ricardo, ¿vas a cerrar o qué?
Sí. Bueno, esperamos más adelante que toda la comunidad pueda participar en estos seminarios. Estamos haciendo pues estos de prueba. Y thank you very much, Courtney. Muchas gracias, Mauricio. A todos los compañeros que tengan pues el placer de conocer toda esta información, y nos vemos en una próxima. Hasta luego. See you later.
Bueno, muchas gracias. Thank you, Courtney.